What was the problem we left off yesterday with? Were we doing something? Oh, the quiz? Okay. We did something with percent. All right, we'll try something.
Here, percent position, percent yield or something. Well, like, it was like a mixture.
Mixture, right. What was a mixture?
Mixture was fluoride, and then like something else.
Oh yeah, okay, yeah. All right. Let's do another mixture problem here. All right. The next example would be, how many pounds of air is required for combustion of 1 pound of methane. Okay, here we're going to assume that air is 80% nitrogen, 20% oxygen. When I say 20% O2, is that by mass or is that by mole? Do you think? So that's the first question we're going to ask. Is this, if this is a mass percent versus a mole percent, those are the two types of percentages that we deal with. If there is a mass percent, then we have 20 pounds or whatever, 20 grams or 20 out of 100 in terms of mass. And so we could do 20 pounds of O2 for every 100 pounds of air. Or we could do 20 grams of O2 for every 100 grams of air, or kilograms, whatever you want. It's the same ratio. However, if this is a mole percent, then it's different. In terms of mole percent, it would be 20 moles of O2 for every 100 moles of air. And so it's a bit different. In other words, mole percent would be like this. We're talking in terms of molecules. So if I had, let's say, 100 trillion air molecules, 20 trillion of those would be O2. Or if I had 100 air molecules, 20 of those molecules would be O2. That's what a mole percent. Except we're looking at Avogadro's numbers, so 100 moles of air for 20 moles of O2. So what do you guess this is, a mole percent or a mass percent? Now, it's hard to figure out because, it's not specified. It should be specified, and you really don't recognize if it's a mole or mass percent just by looking at it. So what we might do is we might just take a look at it here. Do you know what it is? A mole or mass percent? It turns out, if it were mass percent, it'd be easy. But now this would be like an advanced problem because it's not mass, isn't it? It's actually a mole percent. So. Well, that's okay because, at the heart of stoichiometry is a mole-to-mole conversion. And so here we have just a mole ratio. We can always do a mole-to-mole conversion in the center. So we could go from moles of air or moles of O2 to the other. Problem is we don't stop there. We need to go a little farther because we need to know the molar mass of air. Do you know the molar mass of air? Molar mass of air it's a mixture, you know, and so it's a bit complicated, and so but we can figure it out, and so this is the way we do it. So how many pounds of air is required for to complete? Well, any stoichiometry problem, we've got to start off with a balanced chemical equation. So let's go ahead and get it. Methane, what's the formula for methane? CH4. And then when we do combustion, we react it with oxygen, pure oxygen, to form carbon dioxide and water. So let's go ahead and balance it. I got one carbon, 4 hydrogens. So I'll need how many waters? 2 waters. And that gives me 2 plus 2 is 4 oxygens. So I just need 2 O2s, and that's balanced. So this was not too bad to balance. You know, as far as states go, methane's a gas, O2 is a gas, CO2 is a gas, but water is a liquid at 25 degrees C room temperature. All right, so what I'm going to do is this. You know, sometimes we can come up with some kind of strategy. So if I start off with pounds of methane, I probably want to go from pounds to grams or kilograms. You know, I know the conversion for kilograms, or I know the conversion for grams too. But we'll go from pounds to grams. You don't have to have it memorized because that's one of those ones I said you don't have to memorize, right? So we'll go from pounds of methane to grams of methane. Grams of methane, then we could go to moles of methane because we can figure out what the molar mass is and figure out how many grams per mole that is. And then from moles of methane, we could go to moles of, well, it's a 1 to 2 ratio here, so we can go from moles of methane to moles of oxygen. It's a 1 to 2 ratio, so we'll go to moles of O2. From moles of O2, we can go to moles of air. But how are we going to get from moles of air to grams of air? We need the molar mass of air. And so we want to go from moles of air to grams of air, but what is the molar mass of air? Okay, if we can get grams of air, then we can get pounds of air. Well, we know how to calculate molar masses. Molar masses are pretty straightforward. So, you know, what the molar mass of air is this. It's a mixture. Can we get the molar mass of a mixture? Is that even possible? Yeah, it is possible because if you think about the average atomic masses are the average mass of a mixture of atoms. So for example, chlorine. You know, chlorine has 35 U atoms and 37 U atoms. And the atomic mass is 35.5. It's 35.5, it tells me it's 75% 35, 25% 37. You know, it's the average. You guys remember doing those calculations? Well, it's the same thing for air. You know, what is the average mass? And in fact, it's the same formula that we use for atomic mass. And so the molar mass of air is just a weighted average of the mixture. So the molar mass of air is going to be the percent. What percent oxygen is it? Well, it's 20%, so it's 20 out of 100 parts O2. Well, what is the molar mass of O2? Well, each oxygen is 1600, so it would be 32.00. It's 32. So 20 out of 100 parts will be 3200 grams per mole, or U per molecule. And then 80, I'm making an assumption, this is not going to be that accurate because air, if we nail down the composition of air, you know, air is actually a mixture of many gases, not just O2 and nitrogen, and the percentages are off. You it's actually less than 20% oxygen. And it varies, but for the purposes of us, it's easy to calculate. If we have the composition of air, actually, let's see how far off we're going to be. I'm making an assumption just to simplify the calculation because it's all right. I'm going to accept this bit of error, or bit of uncertainty in here. But let me just give you a more exact concentration. And the concentration also depends on the relative humidity of the air as well, because depending on how much water vapor is in air, will change all the other percentages. So projector is having a crash. Moment. Well, so they have composition of dry air and composition of air based on relative humidity. Computer is not. Actually, let me redo this here. So, just restart this. It could be in our book. I don't recall seeing it, but let me just double check. It's in our book here, and then we can get a more accurate value for it. 85T. Yeah, it's not, unfortunately. Well, anyway, so if we had the better percentage, then we just add more terms. Let's say it's 16.8% oxygen, so we put 16.8 out of 100. Let's say it's 78 point whatever, and then it's 1.2%, et cetera, et cetera. So we just keep adding more and more terms to this depending on how many components there are. So I'm just going to simplify this into a two-component mixture here. And so what is the molar mass of nitrogen? Well, it's 14 point. Yeah, but you got to multiply by 2, so you come out with 28.02. And so let's go ahead and figure out, is the molar mass going to be closer to nitrogen's molar mass, or is it going to be closer to oxygen's molar mass? It's going to be closer to nitrogen. It's got more nitrogen, so I expect the molar mass to be closer to 28 than 32. How much closer? 80% closer to 28 than 32. Does that make sense? Probably. You might be able to do this in your head because the difference here is 4, so it's 80%, or say 25%, so around 29, right? 4, so it's going to be around 29 something. But let's go ahead and calculate it. So I'm going to just calculate the molar mass of air. 0.2 times 32 goes out plus 0.8 times 28. Is that what you guys get? Yeah. These, of course, these aren't very accurate percentages because I'm just rounding those fairly. So about 29.4, grams per mole. So if I had a mole 6.022 times 10 to the 23rd molecules of air, 6.022 times 10 to the 23rd molecules of air, 80% of those molecules would be nitrogen, 20% would be oxygen, and then how much would it weigh? It'd weigh 29.4 grams. If these were the correct percentages, that would be it. Those aren't. I'm just telling you right now, they're just ballpark percentages, but that's good enough for us. Here. All right, so I think we have everything we need to do this stoichiometry problem. So let's go ahead and set it up. So when I set this up, I'll just start off. Now, how many sig figs? Well, this is kind of a hypothetical type problem. So, one, it could be exact. I'm not going to call this 1 sig fig. I'm just going to say infinite sig figs. And exactly 1 pound of methane, approximately how many pounds of air do I need? And so here, exactly 1 pound of methane. So I'm just going to go with infinite sig figs here. I don't want to round it too heavily. And so then we need the conversion, for either pounds to kilograms. Do you guys recall what the pound to kilogram? Or pounds to grams? Pound to grams is 453.6. Or, your book says 454, I think, but we'll just go with 453.6 grams per pound. That's not exact. So now we have grams of methane. From grams of methane, we need the molar mass. Carbon, what's the molar mass of carbon? 12.01. Then we have 4 hydrogens, which is going to give us 404. So this gives us 1605. So there's 16.05 grams of methane in a mole of methane. And so here, grams of methane cancel, and that leaves us with moles of methane. So now we're in the center of the stoichiometry map. And we have the mole ratio here. It's a 1 to 2 mole ratio. So we know that there are 2 moles of O2 for every 1 mole of methane. Now, what I do with these percent composition is totally different. In the last problem we did mass percentage, correct? In this problem we're doing mole percentage, so it's different. And we have to be able to do both mass percentage and mole percentage. And so in terms of mole percentage, then it's 100 moles of air for every 20 moles of O2. So the moles of O2, moles of methane cancel, and that gives us moles of air. And so I need to know how much a mole of air weighs. And we just calculated over there. A mole of air should weigh about 29.4 grams. I'm just going to use 2 sig figs for that, but I'm going to carry an extra digit, 29.4 grams of air per mole of air. So this would be a doubly hard problem because we got air as a mixture. Not only that, we have to calculate the molar mass of a mixture, which is a bit of a pain. But since air is such an important mixture, it's not bad to know this. Okay, so we got grams of air. Now we want to go to pounds, so we're just going to go 453.6 grams per pound. So 453.6 cancels here. Grams cancel, and we're left with pounds of air. So if I have 1 pound of methane, how many pounds of air do I need to burn that? So let's see. I'll just go across the top. 2 times 100 times 29.4. 2 times 100 times 29.4. Then I'll go across the bottoms. Divided by 1605. Divided by 20. I get this. 24.23. Actually, I'm only allowed 2 sig figs. 24.2 pounds of air. Is that right? 1 pound of methane requires 24 pounds of air? For every pound of methane, I need 24 pounds of air?
Did you divide the...
Did I do that right? sounds so right. But what you want to do is you want to double check the calculation, which I'll do right now. So 200 times 29.4 divided by
I got it.
5 divided by. Did somebody get a different number?
Yeah.
What did you get?
I got 18.3 because if you multiply them on the top, you multiply them on the bottom, and then you divide them.
Okay, well, actually, I just redid the calculation. I get 18.3. 18.3, I redid it too. Anybody else? Everybody get 18? All right, 18. Well, it looks like the calculation set up correctly, so I guess that's right. For every pound of methane, we need 18 pounds of air. That's a lot of air, seemingly. Well, all right. 18 pounds of air.
So,
Yeah.
do you remember how you did the percent conversion right there for the molar mass? Right then, you're just about to erase.
How did I do that?
Yeah, how'd you get through the calculation?
Oh, how did I do the calculation?
Yeah.
I mean, just this part here?
Yeah.
Set it up?
How you got 29.4?
How did I, well, I just took 20% of 32
And you added 80% of 28.
and then 80% of 28 and just added them together. Yeah. But this is calculator one I used. Didn't bring my other calculator. My other calculator is sitting in my office. I should probably grab it.
Did the 2 moles of oxygen per 1 mole of methane, that came from the equation that we balanced?
Yeah.
Okay.
It came from the balanced chemical equation.
Okay. I have that written down.
You know, and I mean, the amounts seem kind of funny. This is why, you know, when you look at a chemical equation, you know, it's a 1-to-2 ratio, methane to oxygen, but methane and oxygen weigh totally different amounts. You know, oxygen weighs 32, methane only weighs 16, you know, so it's about half the mass. And so I expected, well, I don't know, it still seems off. You know, because it still seems off. Oh, it's because it's 2 O2s, that's why, maybe. Because how much does methane weigh? 16, and O2 weighs 32, but I have 2 of them, which is going to be 64. Now I see, in terms of mass ratio, it's 64 times. Well, actually, what's 64 over 16?
64 or 16 is 4.
4? Right? Yeah. 64 divided by 16. It's 4. Oh, I got it. So, for every pound of methane, I need 4 pounds of O2, but I'm not dealing with O2, I'm dealing with air, and air only has 20% O2, so now it makes sense. Otherwise, that number seems a bit big, doesn't it? Yeah. And so 18 pounds of air, because a lot of that is nitrogen, which is not reacting. It's inert. Nitrogen we'd call an inert component of air. Yeah. Nitrogen's pretty inert. I mean, it doesn't really react with anything. And so now it seems to make sense, right? Perhaps. All right. Well, let's do another problem just to see this. This one will be a more straightforward problem. How many pounds of CO2 is generated per pound of methane combusted. So if we burn 1 pound of methane, how many pounds of CO2 did we just generate? Okay, so let's go ahead and try this calculation here. Let me just get a quick snapshot.